Let's talk now about normalization. To motivate this, let's look at a regression problem. Let's say we're doing a regression problem where we are trying to compute house prices. So y is the house price. And we have two inputs. So x1 is, let's say, the square footage of the house. And x2 is, I don't know, number of bedrooms. So we're going to use a model that's going to be a very simple linear model. We say f of x1, x2 is equal to, let's say, a0 plus a1, x1 plus a2. Right, so our hyperparameters is a0, a1, and a2. Let's talk about the range of these values. So if we looked at x1, what is a range for a house of square footage? Well, we might say, I don't know, maybe this includes tiny houses, that are 100 square feet, all the way to, I don't know, Bill Gates style mansions, 50,000 square feet. Okay, so we're going to have a number between 100 and 50,000. The number of bedrooms, probably not 0. I don't know if they sell studio houses, but certainly 1. You can get a 1-bedroom house, I guess, a small one. So 1 to, I've never seen, well, I was going to say I've never seen more than 6, but that's not quite true. These big houses, I don't know, they might have as many as, let's say, 50 bedrooms. Okay. So the scale of these numbers is fairly different, right? It's 2 to 3 orders of magnitude different. Let's look at how that difference is going to affect things. So if we look at, and let's use our standard loss of, x and y is going to be f of x minus y squared. Okay, so if we look at the loss with respect to a1, that is going to be, so we have 2 times f of x minus y times then the partial derivative of f with respect to a1. So the partial derivative of f with respect to a1, constant, we just get left with x1. And similarly, the partial derivative of L with respect to A2 is going to be 2 times f of x minus y times x2. So we can see here the gradients are the same except for this last factor. In this case, the gradient with respect to A1 has a factor of x1 and the gradient with respect to A2 has a factor of x2. Well, what does that mean about the relative sizes of these gradients? That means if x1 is several orders of magnitude bigger than x2, then this gradient is going to be several orders of magnitude in this gradient. Let's look at, so a contour plot of the loss as we look at the values of A1 and A2. So let's ignore for currently the fact that x1 and x2 are different magnitudes, and let's say they're roughly the same magnitude. We might end up with a loss that looks something contour. As we're analyzing contour plot, right, everything on this line represents a equal value loss. So these are often used for topographic maps, right? So this might represent a height that's the same height, and then this is a different height, and then this is a different height, and then this is a different height. So this might be the peak of a mountain, or it might actually be the bottom of something that looks kind of like a funnel. We can't quite tell without any labels here. We're looking at the loss whether it goes up or down. In this case, let's assume this goes down. So this is the minimum loss, and then the losses get bigger and bigger and bigger, right? So this might be a line where the losses are equal to 50. And this might be a line where the losses are equal to 40, and so on. If we're at a particular point on this graph, if we have equal gradients, we're going to go in roughly the same directions. So we're going to go in the same, we're going to be going in the same magnitude in each direction. So that's going to tend us to go, let's say here. And now we'll calculate a new gradient and go here. New gradient, go here. New gradient, go here. New gradient, go here. So it's a pretty straightforward or direct path that we're taking on subsequent steps of our gradient descent. So these are similar magnitudes. If we have different magnitudes, so let's say this is A1 and this is A2. And now our contour map is no longer sort of circular, it's more elliptic. And what happens here? This tells us that as we move left and right, as we change A1, our gradients are very high, right? These are steep, whereas when we're going up this way, up and down, north and south, these are more shallow, which fits with our fact that our gradients here are higher for A1 than they are for A2. So in this case, if we start at a certain point here, and we're using our standard optimizer, right, where we just say theta minus equals lambda times theta. And again, remember, thetas are just our A1 and our A2 here. Then in this case, if our gradient in the horizontal direction is very high, right, many orders of magnitude more than our gradient in the north-south direction, then we might do something like this. On our first step, we might go like that, and then like that, and then like that. And really, this is less exaggerated than it would normally be, right? If these are actually 3 orders of magnitude, we're going to make very, very small steps in a vertical direction and these large swings in a horizontal direction. So we'd have a lot of steps that we'd have to take in order to finally get to the middle. So we'd rather have a loss that looks more like this, where our gradients are roughly equal, than a loss like this, where our gradients are wildly different in magnitudes. And what hurt us here was our magnitude of x1 with respect to the magnitude of x2. If these had been roughly in the same ranges, then these gradients would have been the same ranges. And then we would have had something that looked more like this. So our solution is going to be, we can change our scale that we use here for our inputs. We could say, well, we know this one is too big by 2 or 3 orders of magnitude, so let's just divide these numbers by, well, let's say 100 or 1,000, and then there'll be more in the range of here, right? So this would be, if you divide by 1,000, that's from 0.1 to 50. This is from 1 to 50, maybe kind of close. What's a more principled way to do that? Well, what we could do is say, if we know this range, we could just take x1, and instead of training on x1, let's go ahead and train on, let's just say something like this, x1 equals, let's convert this to a range from 0 to 1. So we'll subtract the lower bound, and then divide by the upper bound. And similarly for x2, subtract the lower bound, and divide by the upper bound. And now we have 2 numbers which are both in the range 0 to 1. There's a couple questions that come up on this, like how do we actually know this range? What if we don't have some a priori knowledge of what these ranges should be? Well, we could just look at the training set and look at what's the minimum value of x1, what's the maximum of x1, what's the minimum value of x2, what's the maximum of x2, and then go ahead and do this conversion. So we're going to do this conversion on the training set. We have to make sure, right, when we're feeding this into F, right, we're feeding x1 and x2, that we're feeding normalized, and this is our normalization, this is our, well, currently what we're going to call this is actually scaled. There's a little more normalization we're going to do in a moment. So this is our scaled x1 and x2. So we need to scale the training data. We also need to, when we're doing validation, we better scale that validation data, right? Because we have trained F such that F expects x1 to be in this range. and x2 to be in this range. And if we suddenly put in the original values, then we're going to get very bad results for what our estimated house price is. What else do we need to do? We need to scale the inference data, right? Inference is, once we put this out in the world, let's say this is our Zillow estimator of house price, then when we're actually looking at particular houses that are neither part of the training set nor the validation set, and we need to estimate, we need to go ahead and make sure to scale x1 and scale x2. So this will make things better. However, there's still a little bit of an issue. So let's look at, so we're looking at a histogram of just how many values happen, let's say between 0 and 1. And we could look, let's say, at x1. So this can be x1. And this is, yes, x1. And then we can look at, let's say, x2. So even though they're both in the range 0 and 1, they're still fairly different. Most of the values of x1 are down here close to 0, and most of the values of x2 are close to 1. So we could still have a fairly different scale here. In fact, we could still be 2 or 3 orders of magnitude off. Right? If, for example, let's say how we could get that. If most of the bedrooms were, let's say, 2 and 3 bedroom, right? That's down here around, 0.04, let's say, as on average. And the square footage, let's say 4,000 is a common square footage, then we might be around 0.1. So 0.4, 0.1, well, it's a factor of 2, 2.5 off. If our range, let's say our training examples only went to 10K, then all of a sudden a 4K average is at even higher. So it'd be nice if we could get sort of the means of these to line up. And so the way we could do that is go ahead and zero out the mean. So what we're going to actually do is kind of move this over and move this guy over. And so we're no longer going to use this code. So instead, we're going to go ahead and say x1 is going to equal x1 minus x1 bar. That is the mean of all the values in the training set for x1. And that will ensure that half of them will be less than 0, half of them will be greater than 0. What's more, what we can do is actually adjust the shape of these so that we are dividing by the standard deviation of x1, and then do the same thing for x2. So all of a sudden what we've got is both of x1 and x2 have a mean of 0 and a standard deviation of 1. All right? And so that tells us a lot about how many values are in the range, right? Even though x1 and x2 may not be a normal distribution, right? If we look, for instance, so this is 0, -1, +1, we might have, let's just look, for instance, at a bimodal distribution. So maybe there's a lot of houses down here of this size and a lot of houses here of this size. So certainly not a normal distribution. But still, we are guaranteed a certain percentage of our values within so many standard deviations. So we know probably there are very few values that are greater than, let's say, 5 after we do this normalization. So this is what we're going to call the normalization. And what we're going to need to do is, once we have trained our model, we're going to need to save these values, save x1 bar and save the standard deviation x1, because these are the values that were used for training, and these are the same values that we need to use for validation and for inference. So when we're doing validation, we don't recompute what's the x1 bar of the validation. We use the x1 bar that was calculated from the training data because that's what's used to train the model. So that is the idea of normalization.